Welcome to the SBGrid YouTube channel. Software tutorials by developers, lectures by structural biologists, unique content brought to you by SBGrid.
Hi, everybody. This is Jason Key in Boston, Harvard Medical School. Thanks for joining. Today is part 2 of our CCP4 Cloud. Eugene Krissinel is joining us today from Harwell, presenting part 2 of the CCP4 Cloud series. This is going to be the advanced project development series section. So Eugene, go right ahead.
Thank you very much, and good afternoon, everybody, and many thanks for coming to the second part of this presentation of CCP4 Cloud, which is the next generation front end for the CCP4 software suite. Today, I'm going to give more insight into CCP4 Cloud capabilities beyond automatic structure solution, which was presented last week. And please, no problem if you missed the previous webinar, which was CCP4 Cloud in a nutshell. All concepts today should be clear for you. The system is designed for intuitive perception. If it is not, then we are complete failure anyway. But I would like to stress that I'm not going to run a class on crystallography today. Please don't get this wrong. Therefore, do not expect in-depth analysis of various programs, their input and output, and particular recipes for difficult cases. Not at all. Instead, I will focus on CCP4 Cloud as a tool for solving X-ray structures. And I confess that only a limited slice of its functionality will be actually shown to give just the general idea of how the system works. If you think that you are in the wrong place and you would like to have a more substantial introduction to protein crystallography, just please check into one of the CCP4 crystallography schools. All information can be found on CCP4 website. The webinar today will make use of a step-by-step example of solving insulin structure in CCP4 Cloud using fundamental programs rather than automatic solvers built on top of those, starting from a set of images and target sequences only. The data is taken from CCP4 tutorials. I wasn't able to confidently identify authors of this particular data set, and therefore my apologies to them who have generously donated their data to CCP4 for educational purposes. Most probably it happened some 10, 15, maybe 20 years ago. And now we shall start. Connect to cloud through the special launcher as shown last week, login, and create the new project in standard mode, in difference of auto start mode last time. So give it a short ID, like a Unix ID, and put the descriptive title in here. Make sure that standard selection is on, add project. And now first we want to process images, and ZIA2 pipeline is a good tool for that. I'm not going to bore you with manual image processing. It's a whole topic on its own, really. So we simply start this job as a first one. Give it a custom name just for project annotation. It's nice to keep it understandable, whatever it is. And find images in cloud storage where they're prepared for tutorials and workshops. Just here, from images, insulin, and over there. Now you also know. And select those. 180 images were selected and understood automatically. Now we can actually run this pipeline with all default parameters. In reality, it takes a while, but I, of course, sped up this movie. And final report should appear pretty soon. The report, when it appears, it should be examined to see basic data properties and possible problems or pathologies. And again, in normal workshop, it would take about 30 minutes to go through a ZIA2 function. You can see that it reports the space group, lots of other parameters of the obtained data set, looking into native data set, checking XTriage report, all is green, the data set is good. Just for the workshop, lots of other information and graphs here. All right, and probably most of these indicators are known to you anyway. And in the summary tab, there is a condensed information on data objects that are passed on to subsequent tasks from this one. And the data is described in a way which is standard in CCP4 Cloud, not personalized to your program developer, for example. And also the tab gives names for the created data objects. And this point needs some more explanation. A structure solution project may generate thousands of files, literally, and this results in notoriously cumbersome data logistics. Everybody who worked with CCP4 or maybe other system knows this. Files. And CCP4 Cloud tries to optimize this by replacing files with data objects, which are named uniformly and automatically as shown here. The only bit a user can actually control is output ID, the default value for which can be overridden in task interfaces. An object in cloud does not necessarily correspond to a file. It may represent one of few entities from one file, or be a complex entity including several files which should always come together, for example, coordinates and phases. Surprisingly, not too many object types are required for user to control the structure solution process. There are a few more objects under the hood of the system which are not exposed to user. As a general rule, a job can see objects created by all its ancestors in the branch. All graphical widgets can see objects of specific types as shown here, which makes things a lot easier on comparison with using just plain files. Okay, I hope this is clear. And now we continue our project with preparing data for molecular replacement. We need to import target sequences and find search models. It is always a good practice to import or generate all starting data for structure solution in the beginning of the project, although data may be imported at any point if as necessary and if necessary. So, starting from where we left, firstly, import sequences. Do it from the same cloud storage, single file containing 2 sequences, confirm protein data type, apply and finish, and there is not much what to say about this, really, all simple. And now prepare MR model. It is a good practice to annotate your project with remarks. So put something. Remarks can be put again at any time, anywhere in the project. A few words about what the fuss about model preparation. In different from other systems, CCP4 Cloud really insists and hardly insists that MR models are prepared in a separate step. This is done so because molecular replacement depends crucially on model quality, and therefore coordinates should be brought in best possible correspondence with the target sequence. And even more so, several models may be combined into molecular replacement ensemble, which is really the best way of doing molecular replacement these days. There are many different ways of preparing MR models. The situation is a little bit confusing, and they are represented in cloud by 8 different tasks, as shown here on the right. 4 tasks for model preparation here, and 4 tasks for ensemble preparation from models or from sequence directly in there. Models and ensembles prepared with those tasks can be used equally in 2 phasing tasks, either phaser or MOREP. We now prepare search models for insulin chains with MRPAR software, which is a latest addition to the suite. It's only 2 or 3 months old in the suite. So just finish that remark and add new job, which is MR task pass task from molecular replacement section, and make sure that it takes correct objects on input. The objects can be inspected using the magnifying glass buttons, as was just shown here. And this one for reflections, which are needed for assessing the model. Suppose we are good, actually, there is no much choice, and we run the task. When finishes, it presents a rich report with models prepared from PDB and AlphaFold database simultaneously. The models are arranged by decreasing estimated resemblance to the target structure, such that first models are probably the best ones. As seen, no 100 homologs are found in this case, but there are plenty of quite close hits. Now, after this demonstration finishes, we need to run another MRParse task for making models for the other sequence that we have now selected, like here, and run it. Same story. And while it runs, just give annotation for demonstration only to the previous job. Just a demonstration that title of job may be changed in the tree, like here. Open it up. Inspect the report. Now we have some 100% hits, which is two different perfect models. And LLG value is high here, ELG. That's object name. Inspecting the structure. I don't know how useful it is, but there it is. High ELG 500 implies the model should be very close to the target. And again, just annotated for fun. You do not have it. You do not have to have it, and most people do not do anyway. Now, we can try the molecular replacement from this point on. But they are framed in red, those tasks, which implies they cannot be run. We can click on the red frame button anyway and get some sort of explanation what is wrong. The interface is data-driven. If data is not sufficient for running a task, it doesn't fire up. So in this particular case, it says that structure revision, whatever it is missing, but models, which is other requirement for the task, are there. You can check the documentation on these links and find what is what, but obviously it suggests that you run asymmetric unit content task first. So we have to do it in any case. All right. So let's start doing it. And I think again, to be naughty, I put another remark. Start typing it. And this is it. A few notes about the asymmetric unit. What this is all about, because that's another rigid requirement in CCP4 Cloud. The thing is, structure solution requires two basic hypotheses, which are firstly the space group, and secondly, the composition of asymmetric unit. And those remain hypotheses until structure is finally solved. And they may need changing in any point of the project in a trial and error sort of a process. The space group is suggested at the point of data processing, the ZR2 job up there in the project. And we did not question that choice so far, we just accepted it. Unit composition, asymmetric unit composition, is important for estimating solver content and also for knowing how many sequences can be fed. Regarding the structure revision, the other bit which was missing for the task, it's a slightly different story. Structure revision is best viewed as a box with all the data that describes the current knowledge of the crystal at that particular point of the project. So it's a checkpoint, data checkpoint on the project. Each task in Cloud accepts this box, uses what it needs from it, adds or replaces some data in it, and passes over to the next task. A simple mechanism which automates and greatly simplifies data logistics in the whole system. And also it makes task interfaces extremely laconic, as you will see. Tasks can accept only a single structure revision on input, but they can form more than one structure division on output in rare, very rare cases. And they can accept such a box structure revision only from their direct predecessor. This means that if an old structure revision needs to be used. So you were doing something and then decided to roll back. Then the project just must branch from the corresponding task which produces that structure revision. And again, this mechanism enforces the branch and tree structure of the project, which is quite helpful for overviewing and analysis, maybe even years later. So once the concept of structure revision is understood, the principles of project development in CCP4 Cloud should become completely clear. But let's continue with our project now. We run the asymmetric unit content task now. Just a new job as always. Choose asymmetric unit from suggested tabs. And now we are supposed to give all sequences to the task, which we expect to see in the crystal, and number of their copies in a symmetric unit expected. We do not know this for sure before solving structure. That's the problem. We can leave it an auto choice, in which case the task will try to adjust these numbers to having something like 50% of solving. Not always the best way of doing it. So in this particular case, I would prefer enforced stoichiometry because we solving a very well known structure. With this choice, 1, 1, run task. And then what it comes to, the solution shown in bold, it's a little bit wet crystal. And the other alternative, second choice, is a bit too dry, either 64 or 28%, 30% of solvent. Neither is good, and the gouge shows exactly that it is not quite usual. But it could be an acceptable assumption, and this is our hypothesis for now. And we are driven to it by a probability of Matthews solution of 90% as shown on the table just above. Right. A structure revision is formed at this stage, the first one in the chain. It contains just the reflection data set and asymmetric unit definition. That's all what we know about our crystal at this point. Structure, phases, everything else will come next. And this is our problem for today, to get them into structure revision. So from this point on, we should be able to run molecular replacement. And again, to be naughty, I put a remark that we start a new stage in our project, the molecular replacement itself. All right, add new task. We have a choice of phaser and molrep in CCP4. To be honest with you, if I choose phaser now, the project would be a bit too trivial. So I go to molrep and all the program to give a little bit of trouble and then clean up the mess in demonstration purposes. We should choose the suitable model for molrep, and we choose best models, which are first models in the corresponding task. Task number 5, first model. It's default choice, and in this case, we accept it. But just see what's the choice. It's from all the MR parse tasks which we ran before. Number of copies 1, start molrep. What we see, rotation peak is there, not a particularly strong one, but it is there. However, translation function is not too specific, and this doesn't look too good. Well, our factors probably remain pretty high. We shall see them when the task finishes. I did not cut this part of movie, sorry, to keep you waiting. You see, the translation function is not specific at all. Up and down, up and down, up and down. All right, so yes, our factors are pretty high. But at this point, we are supposed to give it a little bit refinement with refmark. And if our factors go down, then things are not lost yet. So we add the refmark job, run it. And goes down, but not as much as I would like it to be, honestly. Let's be stubborn and feed another chain into this, the other sequence. So we run molrep again. Now we have to go to the full list. MolRep here. Choose another model now from task number 4. Data number 1. So 00401. This is 1. Yeah. Request just one copy and run it. Again, slight peak in rotation function. Not too bad, but not too good either. And I'm afraid no luck with the translation function whatsoever. It looks like it has peaks, but the actual variation between 33 and 35 is miserable. Not specific at all. And to finish this branch off, I still give it some refinement just to make sure that it is a profound failure, although this is obvious. Even at this stage. And this is the proof. It doesn't refine, it doesn't go down, so we have to forget about this. Now the question is, what do we do next? What to do if structure does not phase? There are many reasons why molecular replacement can fail. Usual points to check include quality of models, how close and flexible they are, or whether a multi-chain model should be tried instead, and samples may need to be tried just as well. Molecular replacement programs parameter is another potential point to work with. One can try a different MR program, for example, phase instead of MolRep in this case. Also, checking data for the presence of common contaminants with SymBAT is very useful, very often. We can try alternative space group. And if nothing helps, try experimental phasing if you got an anomalous signal. As you see, this list opens up quite a scope for trial and error work, which can be optimized by expert guessing only. And that's exactly what automatic pipelines, which we considered last week, do for you seamlessly and silently. In our case, the presence of rotation peak but unspecific translation function in MolRep results suggests that the problem may be in choosing the wrong space group. And let's see how to fix this now in CCP4 Cloud project. Finish with Mac. Then we should actually check what's going on with data, going back to ZO2 job. Let's prepare the report. Open up the properties of the obtained data set, scroll down, and here we see that indeed the data can be merged in two alternative space groups with same probabilities, 100% each. These groups are not distinguishable from purely crystallographic considerations. It just cannot be done. We have to try both. And that's exactly what we are going to do now, to change I23 for I213. How to do it? Could be done in multiple ways. We could run, let's say, aimless job to manually scale and merge into a different alternative space group, but it can be done easily by just reindexing. Add new job. Go to the asymmetric unit and structure revision section, and yes, the change asymmetric unit space group task is in there. Selected. The task has some wisdom in it. It knows that I23 can be reindexed only in I213. No choice at all, otherwise it would be. Run it. And new structure revision, which this change space group I213, as you see here from the name, was created. And now we pass this structure revision on to subsequent jobs and start to work with a new space group completely automatically. And we just run the same chain of MolRep and RefMac jobs as before. MolRep, first model, see what it gives. And by the way, task can be put in doc like in your operating system, for quick shortcut access to them. You see how I did it. Now, same peak as before, same rotation function, because this is the alternative space group only, but translation function is now a bit different. There are some promise in it. There is some promise in it. Not such a big promise, but something bites. Okay. Density cannot be good at this point, but it doesn't look crazy, at least. You can see some structural features in it. Close it and then give it some refinement from the dock, as you see it here. And our factors are coming down quite nicely, actually. Right, below 50%. Sounds like a luck. Going down to the next chain, next model. Try to fit it with more rep again. Same rotation function. No difference. You can compare it with the previous job, and it's just the same one. In translation part, now there are peaks. They're clearly seen. So probably we got it. From this supposition, I would run next RefMac with jelly body restraints, which is what's recommended after phasing by RefMac team. It's a special region for that. Use jelly body restraints and give it a little bit more cycles, 100 cycles in this sense, in this case, and see how it works. A really dramatic drop in R factors, and this is a clear indication that the structure is solved. However, the final R factors are well above what we can hope for a data set with 1.6 angstrom resolution, like in this case. So how to further improve structure, what to do after phasing? After phasing, fitted models need to be reconstructed and adjusted in order to improve on compliance with the correspondence with the diffraction data. In plain words, residue types should be brought in full accordance with the target sequence, side chains reconstructed, and main chains retraced in improved phases. After that, any unmodeled density blocks should be interpreted as either missing residues, ligands, solvent, ions, and so on. After the structure is finally refined and validated, it can be then deposited to the PDB. There are many tools for this kind of job in CCP4, and nearly everything from what was said can be done with just CUT and RefMac. But this can be a little bit tedious, really. A more economical solution, in my taste, so to say, is to rebuild the structure from scratch, and then use CUT RefMac for fixing the final bits. And let's see now how this can work in practice. As usual, put some remark that we finished this phasing, and now we proceed to model building and refinement. All right, and choose the model builder. We have quite a few of them in CCP4. Tasks, model building and refinement here. Here they are. They do the same job. They construct structure, build structure in phases in electron density, but do it somehow differently and have advantages in different areas. In this particular case, good data set, high resolution data, 1.6 angstrom artwork would be my preferable choice. So I just selected. And I just want to speed it up a little bit by giving it a few macro cycles to run. We'll run it and see what happens. In reality, it takes a bit of time, but much less than what you would spend doing CUT and RefMac manually instead of artwork. Already below 30%, and it's going down. Now stabilizes, It's a little bit fake because it places dummy atoms, then removes them. That's why this spike again. So it comes down to something like 20, 24% density, then still looks good. But obviously it has unmodeled features, the green ones, and partially modeled with solvent, which is of course wrong, and we will have to fix this later on. Okay, but good enough. The structure revision now contains all needful bits: HKL, the data set, asymmetric unit, structure, and the substructure, which was calculated because there was anomalous signal. It just locates anomalous signal scatterers in the structure. Not used in this case, but maybe useful in other cases. So now you want to further improve the build, and if you're good with RefMac, you can do it all manually, just run RefMac with the right parameters or adjust parameters. Again, this can be done, but a little bit tedious, and therefore I prefer refinement and ligand fitting workflow now, which usually does a pretty good job. It is in my suggested tasks, but you can find it in workflow tab. The last one, which was read a week ago, because it can be used only within a project. So click on it. No ligands, and structure revision takes everything what is needed from the previous job. And it starts. No parameters at all. It finds it by itself for RefMac and other programs which it runs. It fits a few water molecules in addition to those which were placed by R4. And you can see that R factors indeed come down a little bit up and down, but it optimizes other scores as well, such as RMS bond deviations and so on. In the end, the R factors were as good and that good that workflow decided to prepare files for deposition. The deposition task doesn't deposit your structure to PDB as yet. Don't worry. It just prepares MMC files for deposition, which you can download from here and then upload manually at deposition process when you are in it. But what we want to do now, we want to check the PDB validation report, which is a very useful source of information about the structure. And these 5 sliders from PDB, which are probably commonly known to you already, indicate that we achieved not such a bad quality of our structure. Only real space RZ outliers are a little bit there, but nothing terrible. Right. So naively, one could think this structure should be deposited as is here, but there is a remark after deposition tasks, which strongly advises you, please do not deposit it without giving it a thorough manual inspection and checkup. If you remember, there were unmodeled residues that we have seen in density, and those defects, as well as many others there, should be rectified before sending anything to the PDB. And this job is for good. And it is also advisable that the final structure, when everything is done and you cannot advance any longer, is put through the PDB redo web service, which can often improve on an impressive number of points and bring our factors further down. And just give a very quick fix of the structure is the code. Here, I would like to proceed with job with lowest R3 rather than the last job from the workflow and results, and therefore I branch from job 29 here. Look, right click, open job, I'm sorry, and I can run code now from the toolbar, another way of tailoring your project, task by task. It starts, and now I have to locate the problematic place. Here it is. I know approximately where it is. Right, and now I need to remove waters from this blob before I can put a residue in. Delete active, and it doesn't go because I forgot to select waters as type for selected objects here. Now it should go. Precise navigation. Delete all of them without mercy. All right, now it's empty. And we can add a basic residue, which is alanine here, and then convert it into what it should be there. And the shapes suggest it's a tyrosine. Let's do it, and then we have to make it into density. A typical good job. Sorry for boring you with this. Now force it down. Nice. Yeah. Looks good to me. Now these changes need to be accepted. That's what we do. And results saved on the default name in default directory as suggested by could. That's how you do it in cloud. And could be exited with option exit and refine, which will start refmark automatically with previously parameters chosen by workflow. You don't have to reset them manually. And just look at how it goes down. So changes were good. And then, as you see, many other green blobs in the project. More fixes are required. By the way, all the scores are good. There are no bold figures in this table. Everything is in the expected range, but believe me, the structure may be yet improved. Which should be done. Right. So proudly, our factors are down. Now, before I finish with this presentation, I would like to allow myself to some general remarks on the subject. Structural biology is driven by data. And from the application point of view, structural data is what is kept in the PDB. But in reality, PDB structures are only interpretations of experimental evidence or diffraction data from here. The structure solution projects then are links between the evidence and the final interpretation. And therefore, they are part of knowledge generated in course of a particular study. Our insulin project, which we consider to be finished now, is merely a toy on comparison with real cases. Those can involve thousands of jobs and non-trivial approaches. The way the structure is solved is currently retained only in publications, and it is not always reproducible, to say the least. Effectively, we are here in a situation when final results are not that tightly bound to experimental evidence. And the interest to keeping as much data as possible and feasible was growing all the time since the Protein Data Bank was founded. Initially, only atomic coordinates were deposited. Since 1999, PDB accepts structure factors, which were made mandatory only in 2008. And since 2020, PDB accepts unmerged data sets, not mandatory, and not the image data as yet. So the way the structure is solved is as important as the data itself, I reckon, really reckon. Revisiting structure solution project, once you have it, may be very useful for understanding how a particular structure feature were obtained for education, templating, teamwork, and software development. And at the moment, we have no framework for archiving and sharing structure solution project with the data. And this is somewhat what a cloud platform can offer. I don't say that CCP4 Cloud in the current shape is an ideal tool for this, but I do believe that cloud solutions here is the ideal instrument to really retain as much knowledge and information as possible. Last slide, I have put our insulin project in CCP4 Cloud's tutorials today. along with a very similar project presenting experimental phasing technique on the same data. And this is in addition to the MDM2 project from the last week. Feel free to check them out, inspect, and play with running your own jobs in them if you're interested. This takes only Googling on CCP4 Cloud and registering with the system. Takes really 5 minutes. Last but not the least, I would like to express my acknowledgements to many people who contributed to the development of CCP4 Cloud. It is really a fun project which continues to develop and going forward, and it wouldn't be possible without community expertise and collective effort. Funding from BBSRC and CCP4 is greatly appreciated as well. That's all, and I'm open for questions, please.
Questions. So you can raise your hand. So if you use the reaction button, you can click the raised hand button, and it should pop you to the front. I just raised my hand so you can see what that looks like. And then we can unmute and call on you. You can also send your questions by chat. You should be able to send them to any of the hosts. So Pete, Eugene, myself. So any questions? I had one, it's just a minor point of clarification. When you did that insulin MR workflow, did you do a sequential or did you do, when you did 2 rounds of molecular replacement, was the
it was sequential indeed.
Yes,
it was
okay,
sequential.
Yeah, I didn't count, I didn't catch if you did
I showed it a bit too
round,
quickly. When you do second molecular replacement job in the line, it says in the input tab that there is a fixed model and it will be used as a fixed model.
Yeah.
If you don't want fixed model, you have to branch one job earlier.
Yeah. The branching looks like it's very powerful, right? So you can just branch out and you could go, you could refine in 2 different,
It is not just powerful. The whole idea behind branching was that projects should be readable after a long time passed. And it is not possible to do if jobs are put just in chronological order, like in other frameworks.
But you could also use different software packages, right? Like you could have chose Buccaneer instead of R4, right? Yeah. And run each of them to see which one does better.
Absolutely correct. You just run them from the same point, which is much easier to do than displaying files or in a chronological list of jobs. Yes.
Yeah, it looks very easy when you do it. You could just click and this goes this way and this is that one. I mean, of course, you're using the tutorial data, but it looks very. The seamlessness between Coot and the cloud is also really impressive. So the ability to have that local GPU-driven graphical workstation and then like have it just save and go right back up for refinement is
we're actually thinking of rewriting code for a complete in-browser use. Because it works, but it is a little bit fragile on internet connection. We have a mechanism of recovering from code crashes in this system. It is documented, and maybe in a few years from now, cloud will be completely in browser.
Because just what you've shown, Ugly Mole doesn't look that bad. Like as far as, it's not that ugly. I've seen uglier.
You just put salt on my wounds. I also think that the development of new code should start with Ugly Mole, but unfortunately, the developer of Ugly Mole has other priorities.
Okay.
And we persuade them to take on the task.
Yeah, because this should be possible, right? Just to have, I mean, yeah, I mean,
it should be possible, but it all depends on how internal data is organized. Ugly Mole was designed as a viewer, not as an editor. And there is a great distance between those two. They look superficially similar on the screen, but inside they are different on purpose, therefore on taking technical solutions.
Yeah, I think that's clear, right? People use other tools that are more for display, like like PyMole or something, where you can't really build models in PyMole very well. You could, but it would be painful, right? So these things are just not designed for those purposes. Any other questions? Questions about? All right. Well, we can we can wrap it up then. Well, thank you very much for the two-part, Eugene. It was fantastic to see. I had not used the cloud-based tools before, and they're very impressive. It's, you know.
And note that CCP4 comes with locally configured cloud, so you can run it simply as a desktop GUI without internet connection. That icon with airplane sign, which I showed last time, doesn't need the big server. If you want just to try it, just to play it without registering, or you have a sensitive data, you can use that one.
Yeah, I think that's most people's, I think, hang up about moving things up, right? Is that they have sensitive data. They don't want to take chances about necessarily tipping off, like, you know, someone who's maybe working on the same thing, and they might get scooped or something. It would be.
Local clouds prove to be useful as well within a lab, within a university, or within a firm where a network is protected. It's also fine. It is installable and not with a big bloodshed.
Yeah, I can imagine that being very useful for like beamlines, right? So they would have this, and right,
Absolutely.
because yeah, you can collect your data, use the cloud, and then you could move seamlessly to the
Although
real
my
cloud.
vision is even higher than that. It could be a pan-European or Pan-American, whatever, service connected to all synchrotrons. Once data is collected and processed and pushed to your cloud, and you come back to your lab, irrespective of where data was collected, you have it in your cloud account. That would be a fantastic future. Given also that most of data collection is now done remotely, you don't have to travel to synchrotron these days. So you send data to whichever synchrotron is available. It is done, data pushed into your cloud account, you start working with it. Would be fantastic. Yeah. There is a way to that target.
Yeah, I think the storage is catching up, right? So that we would be able to eventually, you know, store all of this data.
That's correct, but it is becoming cheaper and cheaper. When we were starting this project, we were worried very much about storage limitations and CPU limitations and bandwidth limitations. And what? We are not hungry for bandwidth. We are not hungry for CPU. We are not hungry for storage. Having about 2,500 users on the system. And it is just a system. It is a small group, not a particularly mighty center.
Yeah, that's impressive. That's that you could support that much storage. Yeah. Well, thank you very much. I really appreciate it. I urge everybody who's here online, check the schedule. We've got one more on the schedule for PIMO, but we're always adding. So make sure to keep an eye on that. And hopefully we'll see you there. And thanks for joining.
Thank you very much.